I will be sharing some research we did under the umbrella of the ATHENE National Research Center for Applied Cybersecurity in Darmstadt, Germany, in collaboration with IONIX. And specifically, we conducted a study on dangling DNS records and their exploitation in cloud environments. And yeah, this is basically the first work to discover real-world exploitation of this type of vulnerability, which has not been shown before, and it sheds some light on how these attacks are actually conducted in practice. To start off, what are dangling DNS records? So let's imagine we have a domain, example.com, which hosts several services on different subdomains. So in this case, like sub.example.com resolves to 1.0.0.1, and there's some service hosted there. Now let's say the domain owner wants to set up a new service, and for convenience and efficiency, chooses to do this in the cloud. They go to a cloud provider, set up a new VM, which receives a random IP address from the cloud pool, and then the domain owner creates a new DNS record in their own DNS zone to point to this IP address, and now users can access the service via the domain new.example.com. So very simple. Now, at some later point, the domain owner decides this service is no longer needed, releases the cloud resources, so the IP goes back into the pool, and critically forgets to also delete this DNS record that was created in their own DNS zone, which has now become dangling. So this is the dangling DNS record. And since DNS information is public, visible to anyone, it's possible that a maliciously minded individual might see that this subdomain points to a cloud-hosted IP. And if they were to ping that service and see, okay, there's actually nothing hosted at that IP, they could go to the same cloud provider and start creating VMs or create services which are assigned a random IP. And this may take a few tries, but eventually they might be assigned that same IP address that was previously used by someone else. And now the attacker can host a web service or just content in general under the subdomain new.example.com without actually controlling the DNS zone example.com. So they essentially take over this subdomain. This is sort of the classic variant of this dangling record of this attack that has been proposed in previous work as well. And I'll give you one of the takeaways from our study up front, which is that attackers don't really, in practice, play this kind of IP lottery where they just create resources and hope to be assigned the proper IP address, because it's just inefficient and impractical. So instead, they go after virtually hosted resources. And here there's some of the key difference. So with virtual hosting, we have multiple resources or multiple services that are hosted by a single server with a single IP address. And so now that the IP address is no longer like a distinguishing address between the different services, instead the different services or resources are addressed on the application layer using the host name. So you can address a certain virtual host by contacting that host name instead. And so now if a domain owner decides to set up a new resource in this kind of virtually hosted environment, these are things like S3 buckets on AWS or Azure websites, these kind of services. They're typically virtually hosted on a small number of IP addresses. And then if you create a new resource there, you're typically allowed to specify a name for this. And the cloud provider will create the host name for the virtual host and the associated DNS record to resolve this host name to the IP address based on this name that was chosen by the user. And this creates and the domain owner will then create their DNS record to point to this created C name that the cloud provider creates. Same as with the other scenario. But now, critically, when the domain owner again releases this resource and it's deallocated by the cloud provider, and they leave their own DNS record dangling, still pointing as a CNAME record to this new-example.cloud.com, attackers can see this. They can see the DNS record, and because a lot of cloud providers operate in a way that the user-chosen name is used as part of the host name, this user-chosen name is leaked and publicly available and visible to attackers. So now an attacker can go to the cloud provider and in a very targeted manner, specifically re-register the resource with exactly the same name. So they will say, okay, I would like to create a resource with the name new-example. Another cloud provider will say, great, that name is not taken. Here you go, here's your resource. And this will, because this is all deterministic, it will result in the same host name, same DNS record, and because the other record from example.com was still left dangling, it now successfully resolves again to this new resource, which is under the control of the attacker. And they can host whatever content they want under the name new.example.com. Except in this case, this is deterministic, this is practically usable, and this is exactly what we see exploited at scale. And one more takeaway beforehand, before we get to the actual study, is that this is kind of simple to fix. Simply randomize the host names the same way that you would be assigned a random IP. You just randomize the host names, do not allow users to choose a name for their resource. And this kind of solves the problem from the cloud provider's side. This is exactly what Google Cloud does. And by sheer coincidence, we don't see any Google Cloud hosted resources exploited in this manner. So it's only cloud providers that allow this kind of, these user-chosen names. Okay, so that's kind of the main issue. Now I'll tell you how we conducted this study and discovered these abuses. So we started by assembling a large list of high-profile domains from well-known sources like the Alexa Top Million, Fortune 1000, Global 500, and some other lists of like government domains and universities. So all domains with high reputation. Then we used a passive DNS service to discover as many subdomains of these top-level domains or second-level domains as we could. So for those who don't know, passive DNS is like large-scale logging of DNS queries. So you basically have access to historical DNS data, and then you can kind of see like what was queried and derive like the subdomains that exist under these domains. And so now we have a large list of subdomains of these high-profile domains, and we can use the same DNS information to see what IPs and what CNAMEs these subdomains resolve to. And then we take publicly available information on the subnets and the cloud suffixes of different cloud providers. So with suffix, I mean like all S3 buckets are hosted on like s3.aws.amazon.com or something similar. And the subnets are also publicly made available by most cloud providers. So you can see like on what subnets they host which services. And then we simply match these CNAMEs and IPs that we have for our subdomains to those that we observe for the cloud providers. And then we know which of the subdomains are hosted in the cloud. And we assembled a list of high-profile cloud-hosted domains that we can then further study. And what we then did is we took this filtered list of subdomains and periodically downloaded the HTML, so downloaded the content that was hosted on this site. And this is actually kind of also an important part because we are downloading the HTML. We are making HTTP requests, so we're operating at the application layer. And this is a far more accurate way of also determining whether a given service is still available, because previous work has also basically checked availability of services by just doing TCP pings. And that's kind of a problem when you have a lot of virtual hosting going on. The server might respond to these TCP pings, but that doesn't tell you whether individual resources on that server are actually reachable. So you do have to go on the application layer to get like an accurate reading. Right, so we downloaded periodically these HTML samples, and this allows us to track the content of all of these pages over time and identify changes. So just as an example, you might imagine that a resource might be available with a certain type of content, then suddenly it's unavailable, it's no longer being hosted, and then suddenly it's available again. That's where we would go in and compare the content. And if there's like a significant change between these HTML samples, then we can inspect these. So part of this study also involves a bit of manual inspection so that we can verify whether this content that we are now seeing is benign or malicious. So it might be the case that there was a big change that is benign. It's still being still being supplied by the same domain owner. But it might also be the case that we're confronted with gambling advertisements or certain adult content, which would indicate that somebody else is now hosting content under this domain. And then we take these to sort of speed up the process of discovering abuses across this large data set. We extract some signatures. These are simple things like keywords, or like just certain HTML snippets and sitemap size. These are kind of features that we collect, and then we can run these signatures on the rest of our data set of samples and see if any of the other pages sort of host similar content, if these signatures match on other pages. And so this also allows us to correlate similar changes across different unrelated domains, which would be a strong indication that this is a kind of a wide-scale operation by the same entity. So this is kind of what we did, and we did the study over a period of 3 years, starting with about 1.5 million cloud-hosted domains. So the filtered list of cloud-hosted domains was 1.5 million. And over the 3 years, we kept adding some more, so we ended up doubling that number actually by the end of it. And among those subdomains, we managed to find well over 17,000 records or subdomains that were exploited. And yeah, these abuses last from anywhere from 2 weeks to well over a year. So these can go undetected for a very long time because these are kind of forgotten subdomains. And this is quite prevalent among even like top industry leaders, global companies. Yeah. A few more facts on the content analysis. I'm not going to go too much into detail because the more important or more interesting question is what attackers actually use these domains for. And the, I guess, instinctual assumption for most security researchers is that this would be for malware distribution, because you have like a lot of reputable, highly trafficked domains, and users might be more inclined to install some questionable software from these domains. And it turns out that we actually see virtually no malware distribution. And similarly, other attacks, more involved attacks that were hypothesized in previous work also did not really surface. In fact, what we see most, or pretty much all of the abuse that we saw, is black hat SEO, so search engine optimization, and other kinds of traffic generating techniques like clickjacking and similar. And this graph you see on the side is a histogram of the domain age of our data set, so all the abused subdomains. it's kind of clear to see that the vast majority is several years old. And this is not a coincidence because these domains have had, this is why they're being targeted, because they've had time to sort of accumulate a reputation on search engines. And this reputation is what attackers are after. And the vast majority of the abuse we see, so it's like 70 to 80%, is actually Indonesian gambling. So that's like the majority of the content we see. And it's not quite clear why, but our pet theory is that since gambling and specifically promoting gambling are both illegal in Indonesia, this creates kind of a gap in the market that attackers are willing to fill. And so they basically use these reputable domains to create a underground ad network infrastructure, so they can run ads for other sites and get paid for traffic content. And how this basically works is, so we have our original setup. We have Dangling DNS record pointing to a cloud resource, hosting some content. This content will get indexed and accumulate reputation on search engines. Then eventually that service is deactivated. The record is left hanging. An attacker re-registers the same resource and hosts some new malicious content there, but it's still under the same domain as before. And thus, this new malicious content is now inheriting the reputation that the previous content has accumulated, because the reputation is tied to the domain and not the content. And so now attackers will host sort of like lots of gambling-related content on this page. And now when users are search for gambling, the attackers have this highly relevant page hosted on many very reputable domains, and so their pages will rank very highly in the search results. And so users are likely to be directed to these doorway pages, which then lead them to the actual content. And then the more traffic they generate to these pages, the more they get paid. And we have strong indication that this is the case because we looked at a lot of these doorway pages, and we kept running into these URLs with referral codes, which is also like a very common practice in normal advertising networks, which allows the target page to keep track of where the traffic is coming from, so that they can pay whoever referred the traffic accordingly. And if you're interested, you can take some of our top keywords that we found and just throw them into Google. And I think even now, you're still likely to come up with several domains which don't necessarily seem to have anything to do, or don't seem like they should have anything to do with these keywords. And that will conclude my talk. Thank you for your attention.